At least this reference is nice to know because that's a kind of evolution to compute the Fourier transforms. So spectral values, things like that. I mentioned to you a few times they have done in 1965 and 66. No longer the spectrum is computed from the Fourier transform. Fourier transform is the problem, time-consuming process to compute the spectral function, spectral density function. Fourier transform of the correlation function was really, really time-consuming. Then these two guys developed the algorithm. It's not the invention, but they develop into it. Then that saved a tremendous amount of the computation time. So they developed the FFT algorithm. And any signal processing, any digital signal processing, they always reference these two authors. So it's worth to, I think he wrote the paper in 1965. So it's, FFT algorithm, once set, because it's algorithm, after that, they just use a routine to do the Fourier transforms, so but always go back to both of them for the credit. So I did not bother to drive the FFT, but now this year I have a strong desire maybe to introduce you, or you can access a lot of literatures available because everybody's using FFT algorithm. So maybe you have a chance, if you are really wants to work on the digital signal processing, then you can go into that and spend maybe a few days to look into the details. That's why can you see? It's so small. Can you see this? Cooley and Tukey, an algorithm for machine calculation of complex the Fourier series, mathematics of computation, and this is journal name, the volume number, page 1965. Okay. In the next few days, I'm going to send you the chapter 4. I'm looking to details right now for any possible the corrections. Okay, so this is via the spectra via the Fourier transform. This is really direct approach to compute the spectral function before always but minus infinity to infinity and Rxy tau e to the minus j 2 pi f tau d tau. So you have to compute this first. So Rxy first, which is a time domain function, then you throw into the frequency domain functions. And this morning we sit around and talk about the math with one of the graduate students here and Professor Park and myself. Nowadays we have a little bit problem. What problem we have? What phase we have? We try to ignore the past. All the classical math, we try to ignore, just skip it, then go right into the, I think I mentioned to you the other day, right into the modern math. We discussed about that, then that's the wrong way. So to get into the root is so important. To get to the modern math, you have to go through all the histories, how to get to that point. Then you will have really solid base to build the area where you want to expand, develop, or invent the theory. So that's another reason I kind of insist look into the Rxy, which is time domain based, then really study personality of Rxy, characteristics of Rxy, Rxx and all that. Then Fourier transform of Rxy getting into the Sxy. Then of course it takes too much time for computation wise. So then after FFT was developed, then you can really save tremendous amount of the time. Then that's what this topic is. Spectra via the Fourier transform. And by the FFT algorithm, that's algorithm, but I said define. Okay, define Sxy. This is define, I said. Once you define, then you have to prove why this is equal to this. That's a Wiener-Khinchin relationship, as you see in your note, maybe next page, I think. There's a proof that you have to, if you are interested, then you have to work on that proof. This is over there. It's a limit. T goes to, mathematically, T goes to infinity as I mentioned, we never go into the infinity, always a finite, then work with the arrow. And 1 over t, summation, oh, you don't have to use a summation here. You can have just E. Summation is within or replace the E. And X star, this is K. K is any function, as I indicate there, the pair of associated sample record is a pair. So X and Y, like input, output, excitation and response, vice versa. And random or stochastic prop from the stationary, I emphasized here the stationary, which is different from ergodic. But ergodic is, of course, a part of the stationary. Then I put the, what do you call that? It's not the parenthesis. That's a parenthesis, isn't it? Parenthesis. This is parenthesis, right? What do you call this? This is parenthesis. What do you call this? Hey, come on. I'll just call both the parentheses. So for a finite time interval, 0 to time t, capital T we use as a period, okay? Then when you expand the capital T to infinite, it contains all the record, but never be infinite. So define Sxy as limit 1 over t, expected value of x star, xk. K is the sample record, right? That's what we defined in chapter 1 or chapter 2. So this is xk, f t, and yk f t in that function. It's a defining process, then equivalence with the Fourier transform of Rxy is proved by Wiener-Khinchin relationship. It's defined. So this star is conjugate. So over here, x is, this is a case, it's a sample function. And the definition here is, definitions here is a stationary process. And I never cover anything on non-stationary process. So I think we should have some time toward a couple of weeks in end of semester. I'm going to talk about the non-stationary process, then you can really compare. And this is, as I shown here, is 0 to time t, x t, of course this is a sample function k, and e to the minus j 2 pi of tau. I use a tau, so this is not tau, this is a t. Tau or d tau, I use a t here, then I can use a t here. So when you put the star here, conjugate, then this should be the positive conjugate function. And of course y, which is kind of a response function or output function, 0 to y sample function k t e to the minus j 2 pi ft dt. And one of the importance in definition is this: expected value of x star y is the 1 over n summation xk star the yk. Okay. Definition of expected the value cast into this problem. So this is a really definition portion to develop the spectra using the Fourier transform. When you say Fourier transform, this is really fast Fourier transform algorithm directly to go into frequency domain rather than taking the compute the Rxy, then take a Fourier transform. Direct approach. So this is much faster. So this is the way the people uses to get to the spectral function, whether Sxy or Sxx or Ssyy is all same. Then Gxy, what's the difference? Gxy is one-sided spectra. Here, before here, this is a two-sided spectra, Sxy. And the one-sided spectra, the frequency range start from the 0. Okay? So, which means you have to double up the amplitude. I forgot to bring my laser point. So 2 is up here. Gxy, if you look at here, there's a 2 there. Others are identical, but frequency range is greater than 0. Fxy. Or Fxx is the same thing. You replace y to the x, then that means absolute of x squared. Okay. Do you have a laser pointer? I think you should have here. So Gxx is really x star times the x. Then that becomes x absolute square. And if you're going to make a G, that's a one-sided spectra. Sometimes when you read a paper, people sometimes called the G as experimental spectra, which is one-sided spectra. So which means F is larger than 0. I put the same thing over here. This is expected value of a bracket, the definition. I should have put this guy into here too, okay? But so that's what that is. And this approach, Sxy is equivalent to Fourier transform. Boy, so fast. I like this green color. So Fourier transform of Rxy, and this is a Wiener or Weiner Khinchin relationship. I forgot the year they published, very early year they published a paper in 1960s, after really 1965. And equivalence, this is of course same as what we have done, is 1 over t and expected value of those. And if anybody interested, you can take a look at that paper. And some of you already saw this, right? If you pick up from Higyu, you should pick this up. Anybody saw this? You check out from Higyu? Didn't check out from Higyu? So I rate this book. If anybody asks me, this is the best book. And other book by other two books I recommended to read, random vibration relevant book, is really application of this book. So this book, I want you to really check out and at least turn the page at least. Because any signal processing, you need information shown in this book. I guarantee that. So this book is a newly published book. This book, the original book is a thinner book. Maybe I bought that book some 20-some years ago. This I bought in 2000. This is a newer book. It's a second edition. So you will face, as a mechanical engineer and ocean systems engineer, signal processing, you will face one time or another when you go into the research lab or industry. So I don't know how much it costs, but pay attention on this book. And the stuff I'm covering is this year is mostly from this book, and some other book too. David Newland book, which I cover some year. This year I cover from that book and this book, and another book written by Paul Warshing, Random Vibration Relevant book. But this year I emphasize this book, and of course the author, he couldn't spell out everything like this one. Then he referenced other paper. Then source, you know, that's what I'm talking about. Source, where to get it, then you would know. Spectra via Fourier transform, fast Fourier transform. And last Monday, I mentioned to you, maybe derive this particular relationship, inequality. You will face a lot of time the proof of inequality. I mentioned to you even Monday, do some derivations, and I spend a day and a half to make 5 problems for midterm exam. Very simple. If you know, very simple. I mentioned to you when I covered the chapter 2, I clearly said, I give you a definition of conditional probability, right? In an hour or 2 lectures, but I said I didn't give you much on the some sample problem. Then if you understand the conditional probability, you should be able to solve the problem. So I made up one problem for conditional. To really spell out the conditional probability, I give you some simple problems, but you need to think. And others, very comprehensive problem, which you will face. Now first I give it to Higyu to do what? To solve first. He should get 100 point out of 100 point, and I'll check whether. If he cannot solve the problem, something wrong, right? So that's what. Some calculation you have to do. That's what I'm going to do. And some proof I may include. So here is very important inequality. If I move this left-hand side term to the right-hand side term, so in other words, if you move this to the right-hand side, then that gxx times gyy divided by the gxy absolute square. What do you call that? What do you call? Coherence function. We covered the Monday. Coherence function. I briefly mentioned that that's really measure of noise contamination. If this, in this equation set, what's the range of coherence function? What's the range? 0 to 1. If coherence function is 1, what does it mean? It's noise contamination is nothing. If it's 0, then what happens? Full of noise contamination. Vice versa. So here we start to prove this. We start from this equation. Again, if you say, Professor Shin, how do you know that equation beforehand? I don't know. You know, mathematician is always a way to start. And A and B are the constant. And the absolute square, then of course that's a positive number. So greater or equal to the 0, okay? Then what happened? The way we did, this is the absolute square. Then same term right here. Same term here. Twice. But there is a difference. What's the difference? One is a conjugate. The other is real as is, right? So when you have x star and x, for example, is equal to x squared. So A plus B, JB is a C, not a C, X star is going to be A minus JB. So X star X is equal to A minus JB times A plus JB is equal to A squared plus B squared, which is equal to, is this correct, right? Which is equal to X squared. Then you can just do the math. This is straight math, no more than straight math. So everybody will get up to here very easy. Then A, B are the constant. Then this can be reduced down to this equations. Then this portion I left as no turn-in assignment. You can do it in your office and sit down and do that. This is equal to that. please do. Okay? This relationship, very clear. Amplitude, phase difference. When you have x, y variable, yx is equal to that, is equal to. So try this one to prove. Then this, with the information on this, you should have this quadratic equation with respect to what? Quadratic. Because you faced this kind of the inequality before. If you divide everything by b square, this is gonna be a over b square. This becomes 2 times a over b. This becomes 1. Then if you look at, then this is a quadratic equation with respect to the a over b. Then apply discriminant, right? That has to be less than or equal to 0, otherwise you have a root. Shouldn't have a root. In the xy plane, this guy has to be always right at x or the above. The graph is concerned above the x. No roots. Except equality become to the 0, equal to 0. That means the parabola touches on the x-axis. I think that should be. Because I think I'm doing something, then I expect you doing something in your office. So this is what that is. Then discriminant. This. Then this. Why this becomes this? You simply multiply 2. Okay? 2. Then 2 square cancels out. You have. This is really getting into the coherence function. Again, it's not bad. We don't have test fixture. Of course, what do you call noise? In mechanical engineering department, they have the lab, noise and vibration lab. What do you call it? NID? Lab, they have I know all the instruments for vibrations and noise. Again, we'll build up. So, should be able to do next year. But it's not bad. You have in the book, you have all the output, then just give you all the samples, so it's not bad at all. This is a range 0 to 1, not the -1 to 1. 0 to 1. So here, remember, gamma xy square is ordinary. This is, should have put, here, ordinary coherence function. ENC, ordinary coherence function. And this is regarding the input, output. Input means excitation, and the Y output is response, relation. Within the relation, then noise contamination is the problem area. To measure the noise contamination, if it's like a 0.1, then actual data is almost all masked. You don't see real data. It's all masked by noise. then that's very useless, the data you try to analyze it. So this is the good index to measure the noise contamination in your signal. This is the first parameter to look at it, because maybe some wire may be loose in your system. To measure, some parts are loosened up and rattle. That could introduce a tremendous noise in the system. So this is the... Then this complex coherence of function representation is really the rarely used, but very rare number of people use this, but you don't have to much worry. It just square it. It just squares it. If you take a square root here, square root, then gamma xy is called the complex coherence function. Okay? It's similar to gamma xy squared. And of course, it could be a complex here. Then you can represent the real part and imaginary part. Then, which means you can express real part plus imaginary part, or you can use a negative imaginary part, which is same as absolute, magnitude, and the phase difference. That's about only two the representation: magnitude, phase, real part, imaginary part, same thing. Okay. And the gamma xy is this square. It's a phase of gxy. In fact, you know how to use a MATLAB. So when I give you two signal, measure the signal, and convert into the generate ASCII file, that means I have to digitize it, right? From analog data, then digitize it. When I digitize it, analog is really a continuous data set. And when you convert into the digitized signal, then you have to know, you have to determine yourself quite a few different parameters. This is like analog data. When you digitize it, this could be when you digitize it, you have to know delta t. You have to know delta t to digitize it. And you have to know F max, maximum frequency content in the signal. Then you have to know total time to acquire. And you have to do that, you have to know how many the data point you have to select. And you have to know sampling frequency, which happen to be always 2 times F max. So it's not coming with no charge. You have to study a little bit. And we're going to do that next lecture. Basics. One table I'm going to give you which tells all the story. So once you, because all this stuff is coming from this is a digital analog converter. Nowadays everything's all digitized and used information. So that converter you can hook up using your notebook. You can hook up as a module, and everything will pass it through. And that's what you have to have. Then once you do that, then you can using like a MATLAB. Then I can give you this digitized data. Then you can do using the MATLAB. You can compute the gamma xy square, sxy square, all different kind. You can do that. But if you have a lab with the hardware, then with understanding of the theory, you can sit there. You can really using the button. You can really taste the story yourself. That's a little bit more easier. And that's what. But this semester, I didn't make any provision to generate to get the digitize the data. We don't have the means to do that right now, but we can do that. Okay. This is another way. First approach to get the spectral density function is by transform of correlation function, classical way. And second way is spectra via FFT, fast Fourier transform function. That's the second. Recommendation is, of course, the second approach. Get the spectra via FFT. Okay. Third is a spectra by or via the analog filtering. Okay. So here, this is what do you call this? This symbol GXX hat. That's what I call. What does it mean, GXX hat? When you have we use a hat in chapter 2, which is what? Estimate, right? We use that hat as estimate. So this is a GXX estimate. Using the analog, when you receive a signal, by putting the filter with all different the filter value in it, and then the whole idea is to get this in there. Depend on the range of the frequency. You could have many the analog filter. Then when the signal passes particular filter, it will just pass that frequency, small frequency range, the value. Only that filter signal will pass, others doesn't. So you have a whole bunch together. Then as it passes, then it passes for the particular filter range, then it passes only for that the signal value for that particular filter. So remember, remember the simply SXX. If X is, let's say, inch, which means, or millimeters, magnitude is, in this case, is displacement, deformation, inch, right? And I said, if you take the area under here, what would be the unit? This area is inch square, right? Mean square value, I said, right? If this is inch axis, in this case, this is that, right? Area. When you get the area under, I'm going in reverse order to get your correct SXX unit. Inch square, right? So this value is nothing but this value is, make it very thin, of course. So this value, the units, I'm looking at the unit, supposed to be this area, okay, divided by what? To get the unit. This unit of this area is inch square. In this case, I said magnitude you're dealing, amplitude you're dealing with, x is inch unit, deformation. You could be a velocity or acceleration. So area divided by hertz. This should be that. This area. To get area as inch square, you have to, oh, this is not the delta. It's delta F, right? Because this is, so this magnitude here should be inch square divided by hertz. Otherwise, when you take the area, you have to multiply frequency, hertz, then this cancels up. Then you have a mean square value as area. So the units of the vertical axis has to be, in this case, is inch square per hertz, always divided by hertz. Okay, always. It's really always you have to divide by hertz. Otherwise, when you calculate the area, okay, you don't get like a mean square value. Got it? Got it. So the unit in this case should be inch square per hertz. If this is that case, what happens when you're dealing with SXX is acceleration. Then what happens? What's the magnitude, unit of the magnitude? It has to be acceleration square divided by hertz, right? Acceleration square, which it could be inch square, inch per second square divided by hertz. You have to be careful. Spectra, when you look at the spectra, that's what it should be. So this is what that equation, that's why it's divided by the delta F to get the divided by the hertz. Okay, let's look at here. This is analog data come into picture. Then you have a whole bunch of filter with a different, the mid frequency start from like 1, 2, 3, all different frequencies, stack up together. Okay? Of course, you can define this is a delta F, this is F, this is F1, F2, this is delta F, then this frequency, you can have, this is half of the F1 plus F2. So I'm going to set this guy is F simply. So this is F. You can have a similar, delta F usually they're constant, usually constant. Then you will get the signal related to the center frequency and frequency size, F2 minus F1 is delta F. Then of course this is time domain signal. And then thus you compute simply X here, relevant to F and delta F, then you square it. Every filter, you square the magnitude. Okay? You can convert the integration as a summation. Then you average it. Average it. Then divide by delta F. You average. And when you average it, then what do? You have a mean square value. Every filter, you square it, then divide by the delta F. You divide by that delta F here. Delta F. Then you got the estimate, spectral density, estimate of spectral density function. Then you will never get this. This should be good enough, depend on the delta F size, frequency step size. But this case is mathematically true, saying that delta F, make it delta F infinitely very small. Impossible. But quite small we can do. In the computation, you can really slice it. For hardware, you can really slice it. For software, you can really slice it, delta F. But delta F, if you really slice it, then you got a problem. If you really slice it, this guy is equal to 1 over t. T is the total time length. You got a problem. This is like 10 to the minus 3 seconds. Then how much? You need what? 1,000 seconds. You have to sit in there in the lab. How long? 1,000 seconds. So delta F you have. So we have to live within the environment we can handle. I don't want to sit there 1,000 seconds. It's too much. So anyway, estimate is good enough to do. This is via the analog filtering. Nowadays nobody do this. This is now kind of a classical approach, but it's very important to know the past, what we have done. Okay, I'm gonna stop right here. Then we'll continue Friday. Then Monday we still have 1 hour lecture. Then 6 to 8 we have a 2 hour exam. I guarantee it's not gonna take more than an hour. So But that doesn't mean that you have to finish everything in an hour, then walk out. That's a stupid. Why? You have a 2 hour, so it's up to you. Okay, whether you spend 1 hour, 2 hours, you have a full 2 hours to do that. So stay in the understanding the basic things in stochastic process, basic, what I taught you. Then it's a home free. Okay, any questions? My office door is always open. You're welcome to come in to do. Okay, so this is 2 o'clock. You had a lunch, so have a cup of coffee. We'll see you Friday.